Welcome to this coding problem walkthrough. Today, we'll be solving problem number 918, titled Maximum Sum Circular Subarray. This is an interesting problem that challenges us to think outside the box and handle circular arrays effectively. We'll explore various approaches to understand the problem and devise an optimal solution. Let's get started. This problem asks us to find the maximum possible sum of a non-empty subarray from a given circular integer array nums. What makes this interesting is the circular nature of the array, which means that the end of the array wraps around to the beginning. For example, in this circular array, the element after nums, n1, is nums, 0, and the element before nums, 0, is nums, n1. The input is an integer array nums with a length between 1 and 30,000, and each element in the array has a value between -30,000 and 30,000. The output is a single integer representing the maximum sum of any non-empty subarray, and this sum can involve subarrays that wrap around the circular structure of the array. To make this clearer, let's look at some examples. In the first example, we have the input array nums equals 1, -2, 3, -2. Here, the maximum subarray sum is achieved by the subarray 3, which has a sum of 3. In the second example, the input array is nums equals 5, -3, 5. In this case, the maximum sum comes from the circular subarray 5, 5, which wraps around the array and gives a sum of 10. These examples highlight that the subarray with the maximum sum could either be a standard non-circular subarray or a circular one, depending on the array's values. Now, consider the third example where the input array is nums equals -3, -2, -3. Since all the elements are negative, the best we can do is choose the least negative number, which is -2. This gives us the maximum subarray sum of -2. Notice that even though the array is circular, the solution must always include at least one element. Additionally, the constraints of the problem remind us that arrays can be as small as one element or as large as 30,000 elements, and the values of nums will always lie between -30,000 and 30,000. These constraints ensure the problem is well defined across a wide range of inputs. Let's discuss a few more edge cases to clarify the problem further. First, if the array contains only negative elements, the result will always be the largest single negative number. For example, in the array nums equals -8, -1, -5, the result would be -1. On the other hand, if the array contains a mix of positive and negative values, the maximum sum could come from either a non-circular subarray or a circular subarray. For instance, in the array nums equals 5, -3, 5, the maximum sum of 10 is achieved by the circular subarray 5, 5. These observations will help us better understand how to approach the problem and handle different scenarios when working with circular arrays. To solve the maximum sum circular subarray problem, we can explore a few approaches. Starting with the brute force approach, the intuition here is to consider all possible subarrays, both regular and circular. A regular subarray stays within the bounds of the array, while a circular subarray wraps around the edges, connecting the last element back to the first. For each of these subarrays, we calculate the sum and track the maximum value. However, this method requires nested loops to evaluate all combinations, resulting in an n² time complexity. While straightforward and easy to implement, it's computationally expensive and not practical for larger arrays. On the other hand, we have the optimized approach that uses Cadon's algorithm, which is designed to efficiently find the maximum sum subarray in linear time, or n. The key insight here is to handle the circular nature of the array by breaking the problem into two main cases. First, when the maximum subarray sum lies entirely within the array, we simply apply Cadon's algorithm to find this maximum sum. Now, let's address the second case where the maximum subarray sum is circular, meaning it wraps around the edges of the array. In this scenario, the key idea is to calculate the total sum of the array and subtract the minimum subarray sum. By doing this, we effectively include the elements outside the minimum subarray, which represent the circular wraparound. The minimum subarray sum can also be determined using a modified version of Cadon's algorithm. Once we have the results for both cases, we can compare them. If the maximum sum from case 2 is negative, it indicates that all elements in the array are negative. In such cases, the optimal solution is to return the result from case 1, as circular wrapping would not provide any benefit. This optimized approach is highly efficient, running in O(n) time with O(1) space, making it well suited for this problem. Additionally, while there's another potential approach using divide and conquer, it's less intuitive for circular arrays. This method involves splitting the array into two halves and recursively finding maximum sums, but it struggles with the circular nature of the problem and has a slower O(n) log n time complexity. Given these considerations, the chosen strategy is Cadon's algorithm with circular adjustment. It stands out due to its linear time complexity, intuitive implementation, and ability to handle the circular nature of the problem seamlessly. The key observation here is that instead of explicitly calculating circular subarrays, we can use the total sum of the array minus the minimum subarray sum to account for the wraparound. This simplifies the solution significantly and avoids unnecessary complexity. When comparing trade-offs, the brute force approach is simple but inefficient with O(n)² time complexity, making it impractical for large inputs. Divide and conquer, while effective for general maximum subarray problems, is slower and not well suited for circular arrays. In contrast, Cadon's algorithm with circular adjustment is the most efficient, operating in O(n) time and requiring minimal space. It's this combination of efficiency, simplicity, and adaptability that makes it the optimal choice for solving this problem. To solve this problem, we need to understand the unique challenge a circular array presents. In a typical array, the subarray with the maximum sum is a contiguous segment within the bounds of the array. However, in a circular array, the maximum sum subarray can either be a non-wrapping one, which is entirely within the array, or a wrapping one, which spans from the end of the array around to the beginning. For example, in the array 5, -3, 5, the non-wrapping maximum subarray is the entire array itself, with a sum of 7. On the other hand, the wrapping subarray combines the last and first elements, giving us a sum of 10. The goal is to efficiently determine which of these two types of subarrays yields the maximum sum, leveraging the unique structure of the circular array. To find the maximum sum of a non-wrapping subarray, we can use Cadon's algorithm, a well-known approach for solving the maximum subarray sum problem. Here's how it works. We maintain two variables, max_ending_here and max_so_far. Max_ending_here keeps track of the maximum sum of a subarray ending at the current index, while max_so_far records the highest sum encountered so far. As we traverse the array, we update max_ending_here by taking the maximum of the current element or the current element added to the previous max_ending_here. This ensures we expand the subarray when it increases the sum but restart it when it doesn't. At every step, we also update max_so_far to ensure it reflects the global maximum. The beauty of Cadon's algorithm lies in its efficiency, as it requires only a single pass through the array, giving us an O(n) time complexity. For the wrapping subarray, the approach is slightly different. The key insight here is that a wrapping subarray can be expressed as the total sum of the array minus the minimum subarray sum. To find this minimum subarray sum, we can slightly modify Cadon's algorithm. Instead of maximizing the sum at each step, we minimize it by updating min_ending_here as the smaller of the current element or the current element added to the previous min_ending_here. From here, the wrapping subarray sum is calculated by subtracting this minimum subarray sum from the total array sum. However, there's an important edge case to handle. If all the numbers in the array are negative, the wrapping subarray will incorrectly result in a sum of 0. In such cases, we should rely solely on the non-wrapping subarray sum, which Cadon's algorithm already gives us. This ensures the result is accurate for all scenarios. There are several key insights to highlight here. First, Cadon's algorithm is central to solving both the non-wrapping and wrapping subarray problems, with a simple modification allowing us to calculate minimum subarray sums efficiently. Second, the wrapping subarray concept is fundamentally tied to the total sum of the array minus the minimum subarray sum. This relationship allows us to handle the circular nature of the problem without explicitly considering all possible subarrays. Finally, edge cases, such as arrays with all negative numbers, require careful handling to avoid incorrect results. From a resource perspective, the algorithm is highly efficient. It runs in O(n) time since Cadon's algorithm is applied twice, once for the maximum and once for the minimum subarray. Additionally, it uses only O1 space, as no extra data structures are required beyond the input array and a few variables. Let's bring everything together with an example. Consider the array 8, -1, 3, 4. Using Cadan's algorithm, the maximum non-wrapping subarray is the entire array, with a sum of 14. For the wrapping subarray, we first find the total sum, which is also 14, and the minimum subarray sum, which is -1. Subtracting the minimum subarray sum from the total gives us 15. Comparing the two, the wrapping subarray sum of 15 is larger, so that becomes our result. Now, take an edge case like -3, -2, -1. The maximum non-wrapping subarray is -1 with a sum of -1. The wrapping subarray sum is calculated as the total sum, -6, minus the minimum subarray sum, -6, resulting in 0. However, since all numbers are negative, the correct result is simply the non-wrapping sum of -1. The algorithm, therefore, proceeds step by step, ensuring the correct result is returned no matter the input configuration. Here, we define a Python class called solution and implement the method maxSubarraySumCircular. To tackle the problem, we start by defining a helper function called maxSubarraySum. This function is an implementation of Cadan's algorithm, which finds the maximum subarray sum for a given array. Inside it, we maintain two variables, current_max, which tracks the maximum sum of subarrays ending at the current element, and global_max, which stores the overall maximum subarray sum encountered so far. As we iterate through the array, we update these values to ensure we capture the largest subarray sum efficiently. After defining the helper function, we use it to compute the maximum subarray sum for the non-circular case, which is stored in the variable max_Cadan. Next, we calculate the total sum of the array, which will be used to evaluate the circular subarray case. To handle this, we invert the array by negating each element and apply the maxSubarraySum function to find the smallest subarray sum in the original array. By subtracting this from the total sum, we derive the maximum subarray sum for the circular case. However, if all elements in the array are negative, the circular case becomes invalid, as selecting all elements would result in a zero sum. To address this, we check if inverted_array_sum equals 0 and, in such cases, return the non-circular result, max_Cadan. Finally, we return the maximum of the two results, max_Cadan, which represents the maximum subarray sum for the non-circular case, and inverted_array_sum, which represents the maximum subarray sum for the circular case. This ensures that the method correctly identifies the largest possible sum for both circular and non-circular subarrays, giving us the desired result for the problem. Here, we start by importing the necessary utilities and defining our solution class. The main method, maxSubarraySumCircular, aims to find the maximum sum of a subarray in a circular array. To begin, we use Cadan's algorithm to calculate the maximum subarray sum for the non-circular case, storing this value in maxCadan. Next, we calculate the total sum of the array by iterating through each element. This total sum will help us later when determining the minimum subarray sum. To find the minimum subarray sum, we invert the array by multiplying each element by -1, storing the inverted values in a new array called inverted nums. By applying Cadan's algorithm to this inverted array, we calculate the maximum subarray sum for the inverted array, which effectively gives us the negative of the minimum subarray sum in the original array. Adding this value to the total sum gives us the true minimum subarray sum. However, we need to handle a special case where all numbers are negative. In such cases, the circular subarray scenario would not apply, so we check if min_subarraysum equals 0. If the condition is met where all numbers are negative, we simply return maxCadan, which represents the maximum subarray sum for the non-circular case. Otherwise, we return the maximum value between maxCadan and min_subarraysum, ensuring that we account for both circular and non-circular subarray scenarios and choose the optimal result. To support these calculations, we also define a helper method called Cadan, which implements Cadan's algorithm. This method iterates through the array while maintaining two variables, currentMax, which tracks the maximum sum that includes the current element, and globalMax, which keeps track of the highest sum encountered so far. At each step, currentMax is updated to either the current element alone or the sum of the current element with the previous maximum, whichever is larger. Similarly, global max is updated if current max exceeds its current value. Finally, the method returns global max, which represents the maximum subarray sum for the given array. This completes the implementation of our solution. First, we start with the input array nums equals 1, minus 2, 3, minus 2. Our goal is to find the maximum sum of a subarray, considering both non-circular and circular cases. To handle the non-circular case, we use Cadon's algorithm. We initialize current_max and global_max to the first element, which is 1. As we iterate through the array, we update current_max at each step by taking the maximum of the current number and the sum of the current number with the previous current_max. Simultaneously, we update global_max to ensure it always holds the highest value encountered so far. For minus 2, current_max becomes minus 1 and global_max remains 1. For 3, current_max updates to 3, and so does global_max. Finally, for minus 2, current_max becomes 1, but global_max stays 3. Thus, the maximum sum for the non-circular case, max_Cadon, is 3. Next, we calculate the total sum of the array, which is the sum of all elements, 1 plus minus 2 plus 3 plus minus 2, resulting in a total sum of 0. To explore the circular case, we calculate the minimum subarray sum using the inverted array. When we invert nums, we get -1, 2, minus 3, 2. Applying Cadon's algorithm to this inverted array, we initialize current_max and global_max to minus 1. For 2, current_max becomes 2, and global_max updates to 2. For minus 3, current_max falls to minus 1, but global_max remains 2. For the final 2, current_max updates back to 2, and global_max remains 2. The minimum subarray sum can be derived by subtracting this maximum sum from the total sum. Since total sum is 0, the minimum subarray sum becomes 0 minus 2, which is minus 2. Now, we handle the edge case where all elements are negative. In this example, the inverted sum is not 0, so we can proceed with calculating the circular case. The circular case sum is obtained by subtracting the minimum subarray sum from the total sum, giving 2. Finally, we return the maximum between the non-circular sum, 3, and the circular sum, 2. The result is 3. Now consider the input nums equals -3, -2, -3, where all numbers are negative. Again, we begin with Cadon's algorithm to find the maximum sum for the non-circular case. We initialize current_max and global_max to minus 3. For the next number, minus 2, current_max becomes minus 2, and global_max updates to minus 2. For the final minus 3, current_max falls back to minus 3, and global_max remains minus 2. Thus, the maximum sum for the non-circular case, max_Cadon, is minus 2. Moving on, we calculate the total sum of the array by adding all elements together. Minus 3 plus minus 2 plus minus 3 gives a total sum of minus 8. To handle the circular case, we invert the array to get 3, 2, 3, and apply Cadon's algorithm to find the maximum subarray sum of the inverted array. We initialize current_max and global_max to 3. For 2, current_max becomes 5, and global_max updates to 5. For the final 3, current_max becomes 8, and global_max updates to 8. The minimum subarray sum for the original array is calculated as total sum minus the maximum sum of the inverted array. Subtracting 8 from minus 8 yields minus 16. Here, we encounter an edge case. Since the original array contains only negative numbers, the circular case is invalid. In such scenarios, we return max_Cadon directly. Therefore, the output is minus 2. Now, let's analyze a case where the circular sum dominates. The input is nums equals 5, minus 3, 5. First, we determine the maximum subarray sum for the non-circular case using Cadon's algorithm. We initialize current_max and global_max to 5. For minus 3, current_max becomes 2, while global_max remains 5. For the final 5, current_max updates to 7, and global_max also updates to 7. So, the maximum sum for the non-circular case, max_cadon, is 7. Next, we calculate the total sum of the array. Adding 5, minus 3, and 5 results in a total underscore sum of 7. For the circular case, we invert the array to -5, 3, minus 5, and use Cadon's algorithm on this inverted array. We initialize current_max and global_max to -5. For 3, current_max becomes 3, and global_max updates to 3. For the final -5, current_max drops to -2, and global_max remains 3. The minimum subarray sum is calculated as total_sum minus the maximum sum of the inverted array. Subtracting 3 from 7 gives 4. To find the circular case sum, we subtract the minimum subarray sum from total_sum, resulting in 3. Finally, we compare the non-circular sum, 7, with the circular sum, 3, and return the maximum. The final output is 7. To analyze the time complexity of our solution, let's break it down step by step. First, we have Cadon's algorithm, which is used to find the maximum subarray sum for the non-circular case. This involves iterating through the array once, performing constant time operations in each step, resulting in O(n) time. Next, we calculate the total sum of the array, which similarly requires a single pass through the array, taking O(n) time. Then, for the circular case, we compute the minimum subarray sum by first inverting the array and running Cadon's algorithm on it. The inversion step takes O(n) time, and applying Cadon's algorithm again is another O(n) operation. Finally, the comparison and return statement at the end involve constant time operations, or O(1). Together, these steps contribute to the overall time complexity of the solution. When we combine all the steps we just discussed, the total time complexity sums up to O(n) plus O(n) plus O(n) plus O(1), which simplifies to O(n). This shows that the solution is highly efficient in terms of time. Now let's turn our attention to the space complexity. Cadon's algorithm operates in place without requiring any additional data structures, as it uses only a constant amount of memory for variables like current_max and global_max. This contributes O(1) to the space complexity. However, for the circular case, we invert the array, which involves creating a new array of size n. This step introduces an additional space complexity of O(n). In addition to the inverted array, we also use a few other variables, such as max_cadon, total_sum, and inverted_array_sum, all of which require constant space, or O(1). When we combine these, the total space complexity is dominated by the inverted array, resulting in O(n). To put this in perspective, let's compare this solution to a naive approach. In the naive approach, we would generate all possible subarrays for both circular and non-circular cases, calculate their sums, and find the maximum. For a circular array, this would involve duplicating the array and iterating through all possible subarray combinations, leading to a time complexity of O(n squared). By contrast, our optimized solution leverages Cadon's algorithm to avoid explicitly generating subarrays, achieving a much more efficient time complexity of O(n). The key takeaway here is that the optimized solution is linear in time and far more efficient than the naive approach, especially for large arrays. While the space complexity is also O(n), this is primarily due to the inverted array, which is necessary for handling circular cases. Let's now consider how the solution performs under different scenarios. In the best case, where the array contains only positive numbers, Cadon's algorithm is sufficient to determine the result in O(n), and the inverted array isn't strictly needed. For the average case, where the array contains a mix of positive and negative numbers, both Cadon's algorithm and the inverted array computation are required, still resulting in O(n) time. In the worst case, where all numbers are negative, the circular case is invalidated by the condition that checks if the inverted_array_sum equals 0, ensuring the solution remains efficient. Ultimately, the time complexity is consistently O(n) across all cases, while the space complexity remains O(n) due to the inverted array requirement. When solving this problem, there are several common mistakes to watch out for. First, one of the most frequent errors is ignoring the circular nature of the problem. Many candidates treat the array as if it were linear and fail to consider the wraparound condition, leading to incomplete solutions. Always remember that in a circular array, subarrays can span from the end back to the beginning. Next, incorrect handling of negative values is another pitfall. For example, if the array contains all negative numbers, some algorithms mistakenly return 0 instead of the correct maximum subarray sum, which would be the least negative value. Ensure that your solution accounts for edge cases like all negative or all zero arrays. Another issue is overcomplicating the solution. Some candidates unnecessarily duplicate the array to handle circularity, which increases space complexity. Instead, you can use indices and modular arithmetic to simulate the wraparound efficiently. Finally, neglecting edge cases can lead to incorrect results. Single-element arrays, arrays with all identical elements, or arrays with alternating large positive and negative values are all scenarios that require careful testing to ensure your solution is robust. Inefficient solutions can also be problematic. For instance, brute force approaches with n² complexity are not feasible for large input sizes, as they will result in timeouts. Instead, it's important to optimize your solution to n using algorithms like Cadans. This brings us to key interview insights. Recognizing patterns is crucial in this problem. You need to understand that it involves solving two subproblems: finding the maximum subarray sum in a linear array and finding the maximum subarray sum that wraps around. Both of these can be addressed using variations of Cadans' algorithm. Another important point is the trade-off between clarity and optimization. When explaining your approach to an interviewer, start with a simple brute force method if necessary, but be sure to outline how you would optimize it step by step. Handling circular arrays might seem intimidating, but breaking the problem into smaller parts, starting with the linear case and extending it to circularity, demonstrates structured problem solving. Finally, proactively discussing edge cases, such as all negative arrays or single-element arrays, shows that you're thorough and detail-oriented. This problem shares similarities with several related problems, which you might find helpful to review. For example, LeetCode 53 focuses on the maximum subarray problem, while LeetCode 918 directly addresses the maximum sum circular subarray. Other related problems include LeetCode 152, which deals with the maximum product subarray, and LeetCode 363, which involves finding the max sum of a rectangle no larger than k. Exploring these problems can deepen your understanding of related concepts. Now let's discuss alternative approaches. The brute force method involves calculating all possible subarrays, including those that wrap around, to find the maximum sum. While this approach is straightforward, it has a time complexity of n², and is only practical for small inputs or initial brainstorming. A more efficient approach is Cadans' algorithm for linear arrays, which can be adapted for circular arrays. This method has a time complexity of n, and involves understanding both the maximum subarray sum and the complement of the minimum subarray sum. While Cadans is efficient, it requires a solid grasp of how to handle both the linear and circular cases. Another approach worth mentioning is the prefix sum method. This technique uses prefix sums to calculate the total sum of the array and identify the minimum subarray sum, which helps in handling the circular nature of the problem. Like Cadans, the prefix sum approach has a time complexity of n, but its implementation can be slightly more complex. This method is particularly useful in specific variations of the problem, where additional insights from prefix sums might simplify certain calculations. While Cadans' algorithm is often the go-to solution due to its simplicity and efficiency, it's good to be familiar with the prefix sum approach as an alternative, especially for scenarios where it aligns better with the constraints or requirements of the problem. Great job on completing this problem. To wrap up, we reviewed the key aspects of the problem, including efficient algorithms and important takeaways. Remember, tackling circular array problems helps sharpen your problem-solving skills. Thanks for watching, and don't forget to like and subscribe for more coding tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!